Alright, for this last video in section 13.1, the last video of the quarter, woohoo, we're going to look at problem number 11. It says to sketch the graphs of each surface in R3 and identify the surface. Here A is a positive constant, and I note here that these three surfaces, since they do come up quite a bit if you take multivariable calculus, I said that these are three common surfaces. Alright, so for part A, we're looking at the surface described by the equation z is equal to a minus x squared minus y squared. Alright, so I'm going to start out by sketching the surface described by the equation z is equal to x squared plus y squared. Okay, so let's do that first, and I can do this using traces in much the same way we solve question number 10. Okay, now I'm not going to include all possible traces. I'm just going to highlight a few key traces to help us put together our sketch. So let's look at the intersection of this surface with the xz plane. So that's where y is 0. Okay, so I get the equation z is equal to x squared, which is this parabola here. Now the intersection of the surface with the yz plane, well, set x to 0, so we get z is equal to y squared. So that's this parabola. And now if I want to look at the xy traces, I'm going to include more than just one here, just to help us get a feel for what the surface looks like. I'm going to set z equal to a constant, so I get the equation x squared plus y squared is equal to c. And here, since the left-hand side is non-negative, so is the right-hand side, so c is greater than or equal to 0. Now if I set c equal to 0, so in other words, if we look at the intersection of this surface with the xy plane, well, I'm just going to get a single point. I'm just going to get the origin, because if x squared plus y squared is equal to 0, that's only true when both x and y are 0. Okay, now if I set c to a positive value, then this equation describes the circle, right, centered at the origin of radius root c. So this gives us this family of concentric circles. Okay, so you put that all together, and we're going to get a circular paraboloid. And there are traces. So if I look at the intersection of this parabolic bowl with the xz plane, I get this orange parabola. If I look at the intersection with the yz plane, I get this blue parabola. And then if I cut this bowl with planes parallel to the xy plane, I get this family of concentric circles. Alright, so this is the graph of the surface described by the equation z is equal to x squared plus y squared. Alright, so now how can I use that to sketch the graph of the surface, right, given in the question? Well, the key there is just to note that this equation given in the problem can be written as z is equal to a minus the quantity x squared plus y squared. Okay, so what is this? Well, the negative in front of this quantity x squared plus y squared, okay, that's going to take this parabolic bowl and just flip it upside down. And now this a, what's that going to do? It's just going to slide the bowl up a units along the z-axis. And that gives us this circular paraboloid that you see here in yellow. Cool. All right, so that's part A. Let's check out part B. Now for part B, we're looking at the equation z is equal to the square root of a squared minus x squared minus y squared. Now because of that square root, I can't break things up in a similar way that I did in part A, but nonetheless we can use traces. So if we look at the intersection of this surface with the xz plane, that's where y is 0, I get the equation z is equal to the root of a squared minus x squared. So that's the semicircle of radius a centered at the origin. If I look at the intersection of this surface with the yz plane, that's where x is 0. Okay, I get the equation z is equal to the root of a squared minus y squared. That's this semicircle here, again of radius a centered at the origin. And then if I look at the xy traces, again, just like in part A, I'm going to include more than just one here, just to give us a good feel for what the surface ultimately looks like. So I set z equal to a constant, so I get c is equal to the root of a squared minus x squared minus y squared. And I note here that since c is equal to a positive square root, c has to be non-negative. And I also claim that c has to be less than or equal to a. And why is that? Well, this square root term will be as big as possible when the inside of the square root is as big as possible. And since we have these subtractions here, that's going to happen when both x and y are 0. And this then would simplify to just the root of a squared. And since a is a positive constant, that gives us that c is equal to a. Okay, so c equals a is the maximum value for c. All right, so now if I square both sides and rearrange, I get the equation x squared plus y squared is equal to a squared minus c squared. Right, now notice here that if c is equal to 0, I get the equation x squared plus y squared is equal to a squared. Well, that's the circle of radius a centered at the origin, so that's this outer circle here. Okay, now if c is equal to a, then this right-hand side is 0. And so x squared plus y squared is equal to 0. That implies that both x and y are 0, so I'm at the origin. I just get this single point here, okay? And for all intermediate values for c, okay, this quantity, a squared minus c squared, will be a positive number, right? So this equation describes a circle centered at the origin, right? So we get this concentric family of circles. All right, so if we put this all together, this is going to give rise to a hemisphere of radius a centered at the origin. I'll put in our traces here, right? So if I look at the intersection of this hemisphere with the xz plane, right? That's this green semicircle. If I look at the intersection with the yz plane, that's this blue semicircle. And then if I cut this hemisphere with planes parallel to the xy plane, I get this concentric family of circles. All right, now one other thing to note here, to see that this equation describes a hemisphere but in a slightly different way, is to say, look, first off, if z is equal to the positive square root of a squared minus x squared minus y squared, z in particular is non-negative. Now if you square both sides and rearrange, you get the equation x squared plus y squared plus z squared is equal to a squared. And we recognize this equation as the equation of the sphere of radius a centered at the origin. But because of this restriction on z, we're actually only getting the portion of this sphere that's on and above the xy plane. So in other words, we're getting this hemisphere. So I note that here. This is the portion of the sphere of radius a centered at the origin on and above the xy plane. All right, great. And so now for the last part, this is part C. Okay, it says, well, z is equal to a minus the square root of x squared plus y squared. So I can approach this in just the same way we did part A. So we'll first graph the surface described by the equation z is equal to the root of x squared plus y squared. Okay, I note here that, again, since z is a positive square root, z is non-negative. Now, if I look at the intersection of this surface with the xz plane, that's where y is 0, I get that z is equal to the square root of x squared, which is the absolute value of x. Careful there, it's not just x itself, because x can take on positive and negative values, right? So the root of x squared is the absolute value of x. So there's the graph there. Now the intersection of this surface with the yz plane, well, likewise, right? I get that z is equal to the absolute value of y, because there I'm going to set x to 0. So I get that z is equal to the root of y squared. So we get another absolute value graph. And now for the xy traces, we're going to set z equal to a constant. Okay, so I get the root of x squared plus y squared is equal to c. And again, since c is a positive square root, c is non-negative. Go ahead and square both sides. You get that x squared plus y squared is equal to c squared. Right? And these describe circles centered at the origin of radius c. All right, so if we put this all together, we're going to get a cone. Okay, so I'll put the cross sections in here. So if we look at the intersection of this cone with the xz plane, right, we're going to get these blue lines right here. Right? It's that absolute value graph in the xz plane. Look at the intersection with the yz plane, right? We get these red lines there and there. It's the absolute value graph. And then if we cut the cone, right, with planes parallel to the xy plane, we get this family of concentric circles. All right, and so now, as you probably can guess, just as we saw it in part A, to sketch the surface described by this equation, z is equal to a minus the root of x squared plus y squared. Well, this negative is just going to flip this cone over, and then the a, right, is just going to shift us a units along the positive z-axis, and so we get this circular cone in yellow. All right, and that does it for this video. Thank you so much.